Okay, well, welcome to number 4 of our seminars. Again, I'll note that these meetings are recorded, and I think I've actually got them all up on YouTube now. I'll do this one over the weekend and get that up as well. Again, we'll go through the requirements for what's happening in the next couple of weeks. And just chasing up, has anyone got any unanswered emails or questions that they had that we haven't got back to you on? If not, good. If there is, please let us know and we'll chase it up. Okay, so we've got the market research costing plan due on Sunday, the 29th of May. So please make sure you can get that in on time. If you're having any issues, again, send us an email on that IoT Capstone email address and we can look into it. If what you're doing is something that you need to keep confidential, just also let us know on that as well. Okay, fundamentals have basically been covered of what we need to do in this capstone. It's really down now to your individual project time, so building your individual prototypes or your concepts, whichever path you're heading down. Big thing this week, congratulations on completing the videos. This is the royal we, as in Savash, will be going through them as soon as possible and giving you some feedback on them.
Just a note on that, Ian. So all the videos have been recorded. Have been marked, and
Okay.
I've sent the comments as well.
Did you email the comments or did they up on YouTube?
They would comment as they see the grades because they've built the commenting system now on edX. But they were all very good this time around. We have a tight-knit group, lots of varied different projects. Yeah.
Oh, good. I'll have a look at a few of them since I get a chance. Okay, so this fortnight, use the other students as a sounding board for developing your prototype of your IoT idea. It's a small group, so you should get to know each other a little bit anyway. The market research and costing report is also due. And in the past, because we had a lot more people, a lot more staff actually in these morning meetings, we'd ask you to think about which advisor is most suitable for your project. So I'll just run through very quickly the others who are available to you, along with myself and Savash. We tend to be around the same sort of area, the embedded systems. I probably do a little bit more. Yeah, I'll get to you in a sec, Savash. I probably do a little bit more on the connectivity side, and Savash is a bit more on the hardcore embedded electronics side and the signal processing. And Savash, you had something you wanted to add?
Yeah, just wanted to ask if you don't mind muting your mics when you're joining in, because we're getting a bit of a feedback. That would be great. Thanks.
Okay. As I said, I mentioned. Can you see who's not muted there?
Yes, there's Ian, if you don't mind. I think you can probably
You might be able to do
press the
it.
mute, Ian, because you're.
I can do it.
Cheers.
There we go. Sorry, Ian, I've muted you. You can unmute yourself whenever you're ready. Okay, so just running through some of the others. David McMeekin, if you're doing anything with location-based services, software engineering, what else is he in? Mapping, anything to do with space and how we use it. Valerie is our Python guru. So if you're working and have a tricky little Python problem, it'll be Valerie you want to contact. Yiffy for artificial intelligence, machine learning. Thinking Nazanin is the network person. You would have got to know her quite well in the networking module of this MicroMasters. Thinking quickly, Hannes for anything to do with algorithmic or efficiency designs. So if you've got code that's taking too much time to run, Hannes is the guy to speak to. Who am I missing, Savash?
Did you mention Yiffy for machine learning?
Yiffy for machine intelligence, yep.
Yeah. Oh, and we do have a new staff member, Reza, who specializes in
Yes, of course.
cybersecurity.
Yeah, Reza on security.
Yeah.
and particularly embedded security, or if you want to look at issues around securing your product from the IP perspective, we can also look at that. So let's move to the next one. Just a reminder, the market research and costing plan is 15% of your overall mark, broken up as we can see below. I won't say all of that, but you can see where we're putting the priority. It really is about the products and or services section of it, the SWOT analysis and the industry analysis as well. So it's about understanding where your product fits, and that's really what we'll be looking for. We have some templates available, I think, in the edX material, so you can use those. Or if you prefer, use your own format. We're not particularly fussed how you present it. Do it in your own style if you like. Okay, so what we're going to be talking about this evening is heading towards production. So we really want to have a closer look at how you go from that idea, the concept, start producing prototypes. I was going to say some prototypes that are around the idea of seeing if something will work. You've then got a next stage of prototype, which we call the manufacturing prototype. And this is building something that will look like your end product. This is possibly working and also possibly doesn't work. It can be for the physical attributes of the system that you've developed. You want to build a mock-up of it, look at whether it's actually going to look correctly, look as it should. If it should fit in the environment that you're going to put it, you might do it for testing of weatherproofness, adaptation to other pieces of equipment. So if it's an add-on to something else, and you want to build something that is physically correct, but may not necessarily work. And that we'd term a manufacturing prototype. So to get to these sort of points and to the final stage where you build your production model, there's a few tools that we generally use. And the ones we'll be covering are the software development tools, which is critically important. The tools for building PCBs, how you actually get your electronics down on a physical platform. And finally, something that quite often neglected in these sort of courses, the housings. What are you going to put it in? Almost nobody produces the electronic components to be sitting out on their own. You need to create something to put it in, keep it safe, keep it out of the weather, stop people touching it, etc. So housings is critically important. I'll give you a little example of a housing that was poorly designed and wasn't really thought about very well. One of our research groups designed and commercialized an inverter system for taking renewable energy and feeding it back into the grid. Quite a large device, about a meter cube box, which was intended to be placed outdoors. And as a final thought, they just popped the cables, power cables that went into it, into the top of the case. Now, I think you can see where this is heading. First time it rained, even though we've got a weatherproof seal on that cable, water ran down the cable and got ingress into the box itself and basically destroyed it. And it was a simple oversight that they didn't look at how they were designing the case and the environment it's going to be sitting in. So again, very important to look at case, the housings. And there's a few aspects there, whether you need it waterproof, how many you're going to make is critically important. How durable does it need to be? Is it meant to last forever? Is it something that's disposable, consumable? Different sorts of costs, size, and many, many other things. So first thing we'll look at is the software development. Here's something most people are probably familiar with, the good old Arduino IDE. It's really simple. It's got all these built-in libraries. It's has the ability to build something really, really quickly and get it up and running. You can change platforms. You find the processor you're using is not powerful enough. It's just a simple selection from your configuration, change to a more powerful platform, recompile, and off you go again. Everything's really simple, quick to do, but it is incredibly inefficient in the code it produces. Because it's designed to be all things to all people, it has to have several sort of workarounds to keep that compatibility. And that makes it inefficient in the way it runs and the way it compiles the code. Other options or other things with it that are quite useful is the fact it's open source and you don't have to pay a license fee. It's becoming less common, but there are cases where your development environment requires a runtime to be put onto your board, and that has to be licensed. So you have to pay a license for each and every copy of this program you put out. A great example of this is one that we've just started using. You want to talk a little bit about the Arduino speech and how that library is?
Yeah, sure. So basically, this is a offline independent in a speaker independent voice recognition setup. And the way they have arranged the license for it is there is a separate program that generates a hex file and that ties down to only one Arduino. So when you go and program the Arduino, the algorithm and the way they're doing this, the licensing of it, you need to have that generated hex code, otherwise the code wouldn't work. And that's only tied down to one Arduino. So you can program it, and then if you want to add more devices, you have to pay a licensing fee for that. And they also separate. They also have a separate cost for the overall licensing application, which allows us to modify the types of commands that we want to we want to implement for the voice detection system. So yeah, that's a interesting way to go license out uh, these types of implementations.
And that has to be counted into your cost. If you forget that those sort of costs, you can end up bankrupt very, very quickly. I think it's $7
Yeah,
for each one.
yeah, it's about $7, and that's per board, in addition to the cost of the actual microcontroller.
So it can be a significant cost. And it's not just for those particular one-off type routines. You can find that particularly some development environments like Texas Instruments, they do have a licensing fee as well. So you have to pay for every one that you put out. But the Arduino, with all its drawbacks, um, is open source, so you don't have to pay any of those license fees. It's also not ideal if you're trying to produce commercial level software. So if we look at something that's a little bit more commercial, and this is the MSP 430 that we unfortunately use a lot in our labs. It's a Texas Instruments platform using Code Composer still, Savash?
Yes, that's a code composer. Harun has a question.
Yep.
Yep, Harun, go ahead.
I have a question about the Arduino IDE. How about the direct port manipulation? How effective is it compared to the, let's say, an Atmel Studio program, like from the zero,
Hmm.
compared to, let's say, Arduino IDE environment without libraries as the direct port manipulation? Would it still be feasible?
That's actually what we're gonna be discussing in this slide. If you don't mind, I can talk about it. So
Yeah,
basically, yeah, the main difference, right, going in comparing with the Arduino IDE and something like Code Composer that's a bit more professional, is the ability that you'll have to look inside your registers and monitor the flow of the program beyond just some lines of code. Because we discussed this briefly in the first seminar. With these tight-knit IoT setups, one of the things that you'll have to do is you'll have some sort of a monitoring system. So you're gonna end up in an infinite loop somewhere in your programs, and you want to monitor conditions. So it's a very, very simple example of that is you have to monitor a button press, and that button press needs to turn into an action. Or you're monitoring let's say, a pressure system, and you want it so that when the pressure changes, you want to turn on a warning light or turn or open a pressure valve, right? So with that sort of setup, you need to interrupt the current normal flow of your program. And for you to do that, you need to hold the current state of your program somewhere and go somewhere else, handle a routine, handle a subroutine. In this case, this would be an interrupt, and then go back to be in that infinite loop cycle. And all of this requires a very low level uh, critical management of the code, right? Because you don't want to be in a situation where you have interrupted the program, but you're not able to go back to the original state of it. And because this is such a low level control, we're gonna end up with situation. If you want to write a very optimized code, you'll end up with situation where you need to have that. You need to actually go one level lower than C, and in this case, the highlighted part is you go to assembly and mix C and assembly together in some instances, and that can be for specifically for controlling with those in those low level memory control setups when you're setting up your low power modes to handle the interrupt component, and that's just something that we can't necessarily do with the Arduino IDE. Now, with their 2.0 version, they have started adding these control register monitoring stuff. They're getting a bit better, but I think there's still ways behind the more professional development because that and they're very good for having functional prototypes. But another benefit of something like this is your code is going to be a lot more lightweight compared to the same code on an Arduino. Because with Arduino, you have to upload all of those different libraries that you might not even be using, but because for the sake of ease, they put all of their setup in their core library functions. So your source code will end up actually being larger when you implement it in an Arduino in an Arduino environment.
Yeah,
Yeah.
there's a couple of other major benefits of using a more complex or more professional development environment. Number one is the ability to, as Savash mentioned, streamline or optimize your code. That's not just necessarily for speed, but in the IoT environment, it's very much about power usage and battery life. If you can slow the clocking of the processor down, you have major power savings. So having the code running slower and still being able to perform within the deadlines that you have is a major power saving. And you need to be able to have very tight control over the hardware to be able to do that. High level languages don't always produce the best code. So the ability to insert the assembly language in where you have a particular hotspot, and that's where you spend most of your time processing, and optimizing those areas of code can make a significant difference to the power footprint of your device. The other one is also, of course, to shrink your code size down. Now, that may sound unimportant in the days of terabyte USB sticks and lots of memory everywhere. However, the cost of memory in an embedded systems is still significant. And when I say it's significant, we could use the Apple advantage example. They said that for every dollar of components they put into a device, it adds $100 to the sales price. So if you're spending an extra dollar on memory or an extra dollar on a higher level processor, you're looking at a much, much larger increase in the end price of your product. I don't believe it's 100 times, but that's what Apple came out with. So the ability to write very efficient code, to be able to optimize that code and minimize the memory footprint is very, very important in the IoT because of our restricted resource devices that we're using. And we really want to get our devices down to be as cheap as possible so that you can have lots of them out there. Almost to the point of being disposable in many cases. So this is a more complex one. There's lots of them around. Some of them are very, very expensive. Some of them aren't overly expensive, but they tend to do a bit more than those that are free, such as the Arduino environment. Do we still use IAR, Savash?
Yes, because they keep updating and bringing newer version of IAR, and the good thing about IAR is the free version that you can use. It's only there are two ways. You can use a time limited version that gives you 30 days, but there's an unlimited code size limited version that you can use. So that's unlimited use. It just limits the code size by a certain amount. I forget how big it is off the top of my head, but it's a very good kind of entry point in exploring coding in these sorts of environments, especially looking at the code and the disassembly window, because then you can, as I said, you can do the register monitors. You can see the assembly code equivalent of each of your lines of code. So It's a very interesting environment.
It
Um,
is, and it's got all that real-time capability as well.
yeah.
Because when you're building something, say, for a medical device, you need to be able to ensure that you're doing things correctly, and that you can prove that they're correct and things aren't going to go wrong. So you can never write a bug-free program, or it's very, very unlikely you can write a bug-free program. But in medical device, you've got to be able to prove that your code, if something does fail, it's going to fail in a safe way. And the only way to be able to do that is to be able to inspect the code very closely, which is where you need to start looking at these more complex development environments. Did someone have their hand up, or was I just imagining I saw it flicker around?
No, Arvind, do you have a question?
Yeah, I had a question about this. So when you run this machine code, does it simulate what is happening at the hardware level?
Uh, are you talking about the left-hand side diagram or just
Left-hand side diagram.
so this what it does like a bit in a more updated version of these IDEs, the one that the STM uses, that actually shows you what subsystems within your microcontroller are activated and what parts of it have been highlighted. I think the MSP does the code composer environment does the same. So um, it highlights which one of your different components that you're using. So if you are using the flash memory and say one of your internal clock systems, it'll give you that overview so you can track on the logic side as well.
Yeah, IAR used to, and I'm not sure if it still does, have a full emulation environment, so you can emulate what's actually happening on the hardware within IAR, but only on the
Yeah,
processor, not on the peripherals.
yeah. It was the IR just on the processor itself.
So that's the first part. When you're deciding to develop your system software, it's fairly important that you choose the correct development environment. You can do early prototypes or things that are just going to be very low product runs in things like the Arduino environment. But if you start to head towards larger production runs, where you need to get that efficiency and minimize the cost as much as you possibly can, or in medical systems, you need to start considering going to these more complex and usually more expensive options. So you're writing your software. It works on your development board. Now we want to make something that's a little bit more hardware orientated. So we've got a couple of prototypes that we've built in-house here. The one on the left is what we term a sticky tape prototype. And it's basically a whole bunch of off-the-shelf boards all wired together. Sticky tapes usually to hold them in one place and put in a little 3D printed box, which we'll talk more about later. That one is actually, excuse me, an inertial measurement unit that we built many, many moons ago, with a Bluetooth or wireless connection. I think that might be our standard wireless. Um, this was very good for proving a point. However, because as you can see, there's lots of wires hanging over it, there's lots of separate boards, it was hard to keep physically together. Um, with movement, and this thing was used to measure movement, wires would break and boards would come apart, so it was incredibly unreliable. Sebastian, you used some of these in your early PhD work, didn't you?
Yeah, so and you can imagine another problem with something like this is because we were using all of these off-the-shelf components, it was a bit bulky. So I was using with some setups to capture hand movement of children, so that in some cases, especially with infants, the package ended up being bigger than their hands. So you can imagine. Uh, but as a proof of concept, as an initial uh, starting point of getting some quick data, get your understanding of the individual components, that's where we have to start.
Yeah. So it was great to prove a point. The principle of the device, the way we wanted to work it, the software, it all worked, but it wasn't reliable and we had to change. So we moved on to a new design. On the right, there's a couple of other devices I developed again a few years ago, showing how you should end up with a prototype. These were still prototypes, but they were at a low level production run. The one on the left PCB is a text-to-speech synthesizer that we built that actually converts strings of text into human-ish like speech. And the one on the right is an ultrasonic wayfinder for people with vision impairment, and basically works like a sonar system to let blind people know when they're about to walk into something. Um, these were designed in-house, all built in-house, um, and were basically the final level that we got to, even if the wayfinder device has sticky tape on it at the moment. We got rid of that when we built the housing. But this is what we want to do. We want to get from that one on the left where it's a whole bunch of off-the-shelf things stuck together to something that can be packaged and built in larger runs. As you can imagine, the one on the left will be very hard to mass produce because the amount of handling you'd have to do to actually solder everything together. Whereas the ones on the right can be produced automatically on robotic machinery. So how do we get there? Again, we've got many, many options. We can start with something free and easy, such as Fritzing. Wonderful name. Fritzing is a really good package. I'm not sure if you've used it, but we did mention it a couple of times in the IoT course. It allows you to draw the schematic. I don't know if you can see can you see my cursor?
Yep.
Yep. Good. So we can start with the schematic, the actual logical diagram of what we want to build. We can then put that into a simulation, but it's limited on the kind of platforms it supports, and make sure it actually runs with our code, which is up here. And from that, we can pretty much automatically generate the PCB layout, which is down here. It doesn't usually auto route perfectly, and you'll want to adjust it, but it does give you that ability to fabricate, to design the PCB ready for production. I'll talk more about the production bit later, but you'll notice down here we've got a fabricate button, which links off to one of the preferred PCB suppliers that Fritzing use, and allows you to go through this whole stage, send it off to be produced, and a few days later you'll get your PCBs back. As I said, Fritzing's free. It's not limited in any way that I believe, and for small boards and simple designs, it's really, really good. And you can go through the whole design process with it. Next sort of level up, and these are not the only ones. There are lots of them in the free, and there's lots of them in the semi-free or have free versions. The next one up we'll look at is Eagle, which is from Autodesk, AutoCAD, SolidWorks, I think, as well. And this is sort of the next level up, and it allows you to do a few other things, but they do have a free version for hobbyists. Limits you to 2 layers. I think Fritzing will only handle single layer boards, both sides, but single layer. And it is quite scalable. So you can start with something simple in Eagle, start paying the higher fees, and get more and more features as you go along. So only pay for what you need. It is quite good. I haven't used it a huge amount, but I know the students, our students tend to like it. Would you say this is the most popular one amongst the students?
Yeah, there's this one, and then there is another one, Easy EDA. I've sent a link to that in the chat. That I think that one links with PCBWay, because PCBWay and JLC PCB have become pretty popular as PCB manufacturers in China. So they now have their own similar to Fritzing. But I think Fritzing is another one of the manufacturers. But Easy EDA is also pretty good, and it also has a web versions that so you don't have to worry about operating system specs. Eagle is very good as well. I believe the free version also does the 3D mock-up of your design, which is available in some of the more expensive ones.
I think it does a few of the other rather neat little things like the heat map, so it'll look where your
Yeah.
power consumption is.
Mhm.
It's got a better auto route. It'll work on more complex circuits and give you a better starting point with the auto route. And it's cross-platform as well. So you can see on this one, it's running under Ubuntu, I think. but they have Mac and Windows versions as well. So you can design on one and then transfer your designs to multiple different platforms if you need to. And then we can move to the cream of the crop. This is probably one of the best ones. Altium, what used to be called Protel. We can give it a plug because it's an Australian company. They're based in Tasmania, which is a little island off the southeast coast of Australia. And this will basically do anything you want. It's a full-blown system. From memory, it's around $10,000 Australian a copy. So it is not cheap by any means. It's incredibly complex to use. We have Protel come in and give courses to experienced PCB designers in how to use Protel, Altium. Part of a deal we've got them where we get free licenses. But it's a week training for experienced PCB designers to learn how to use their platform. It does the 3D rendering of your board design. It has all of the features. It also will do some frequency measurements, so looking for crosstalk on tracks. It will give you the correct weighting for the current draw of components and many other things, and auto routes quite nicely on its own. I wouldn't even suggest looking at this unless you have a very, very complex system, such as we were talking about when we first started with how many components? Lots. But it is good. It's not impossible to learn to use. I used to use it quite intensively when I was the technical manager for the school, and we were designing all our own boards, like the famous click boards that everyone loves.
Yeah.
Savash will get that joke. Right. So as I was saying, a lot of these packages link off to particular PCB manufacturers. They use a standard format generally called Gerber, and you'll notice that funny little machine sitting up in the corner there. That is a Gerber. A Gerber was a machine used for cutting vinyl back in when did I work with these? Trying to remember.
80s?
In the early 80s, I suppose, mid 80s.
Oh, that's right.
Yeah. And it was the very first sign writing robot, and they've got a knife in there that just cuts the vinyl so you can get those vinyl letters, and it totally destroyed the sign writing trade. But because it's about cutting vinyl, the same as you would cut a track, they used the Gerber file format to standardize how you lay out or how you transfer PCB files. Just a little bit of history for you. So a lot of them will link off to these manufacturers, and I think Fritzen gives you a few choices actually of which one you want to use. But be very careful of this. Number one, they are and can be incredibly cheap. The PCBs back here that we did, these ones here for the text-to-speech, we got made in China from the Gerber file. It cost us more to ship the boards out than it did to manufacture them, even with the chips placed on it. However, when we got our first 25 of them, I believe only 10 or so worked. But it was so cheap that it didn't matter. Right? We could either fix or throw out the faulty ones. They did other things such as go back to it again. The crystal here, they didn't put the one in that we specified. They used one that was cheaper, and it was too high to fit in the case that we'd built. Right, but they thought, it doesn't matter, we'll just put whatever's cheap on there. So the problem with using some of these suppliers is they may be very cheap, but quite often they'll have very, very poor quality assurance. So you need to balance that out. Is the price so low that you can cope with the failed units, or do you want to make sure that you get a high quality and very few failures? And that is very dependent on the individual cost of the component. If something is done wrong, you've made a design error, you've got to think about that as well. So how many do you get manufactured at one time? Usually you'd start with, like we did with that text-to-speech, a very small number to begin with. You make sure that your design worked, not so much their production, but the design worked. And if it didn't work, fix it, change the prototype, get another batch made. So that's fairly important. You have other options. You can get the components placed on by the PCB manufacturer for what's usually a reasonable sort of cost, slight addition to the cost of the components. But in many cases, the PCB manufacturers can buy the components much cheaper than you can. So it sort of balances out, and it might turn out to be that you get them to fully populate the board as well. Other options you've got in there, the silk screening. Do you want the tracks to be covered by an epoxy? Do you want it all bare, open copper? Different types of finishes, different thicknesses of PCB, lots and lots of options to look at and need to be considered when you're actually ordering the board. Anything you want to add to board manufacture?
There's also the fact that you can also get the stencil for the
Oh, of
PCB,
course.
which
The
will,
stencils, this.
yeah.
You mean the stenciled letter or the stencil?
You know that there's the normal stencil, so we can for some of the surface mount stuff, you can use it to do the printing. So it's like a map that you put in. But before we had the component shortage, our standard answers would be, well, because it's so cheap, you could just always order your PCBs with populated, which means they do the machine solder all of the surface mount and the regular components in there. But because of the current chip shortage, one of the things that we've had to do at Keratin is sometimes pay for an expensive development board so we can grab expensive sensor that's just out of stock in a standalone format. So solder out the sensor from the dev kit and put it, or solder out a microcontroller that we need with the specific specs, and then solder that on the prototype. So the sensors and become become pretty handy these days.
Yeah.
Yeah.
So this is the design package for one of the PCBs that we did at some point. And it's good just to see the price. If you wanted in 5 to 6 days, this was $185 for quite a complex board, 6 layers, which is a lot of layers. Fairly heavy PCB, so this is where you choose the thickness of the substrate and the copper tracks, your minimum spacing, so that's important for isolating and heat. Different colors. What else have we got up there? Yeah, the copper weights, whether you want an aluminium board or a copper board for the conductivity. Lots of different options you can do, and we can see we get the price, quick shipping, and for some reason I'm not sure why I had that particular one in there, but yep, we've got our price there. Put it in, and you get them within a week. So not bad service, much better than many, many years ago. Okay, so moving along, very important, the housings. And I mentioned that this is a critically important thing, which is sadly neglected by some manufacturers. If you look at the extremes, you've got Apple, who spend vast amounts of money ensuring that all of their devices are really well packaged and neat and pretty, and they charge a bit extra for that, a lot extra for that. Whereas you look at some of the cheaper rivals, some of the clone type laptops, and they're really tacky packaging, things don't fit together, etc., and they don't last quite as long. But anyway, going through for our purposes, there's several general categories you can look at. There's the Jiffy box, which is this standard, usually rectangular type box that you can buy from any electronics store. They are very cheap. They are very ugly. You can get them weatherproof. You can get them in different sorts of industry standard of quality and environment. So outdoor usage, indoor moisture proof. You can't get any for that are actually waterproof, as in to work underwater. But they're handy for something that's a small run, or a device that you're going to hide away. It's not going to be generally seen by people. And they are, as I said, very, very cheap, particularly when you start to buy them in large numbers. The one above it here is our standard sort of 3D printing. Inside there, I think, would be a Raspberry Pi, wouldn't it? These are great for your initial production run, not production run, your initial prototype run. You can check to see that everything fits together correctly. You can try it for instance, the way you hold things. So I have no doubt that I can't see me, but I hope you can see my controller there for the Oculus. If you 3D print something like this, it's nice and quick and easy to do. You can see how it feels. You can make sure that, that's my left hand one, make sure it actually fits the hand correctly. It's going to do the job that you want. But being 3D printed, you've got a couple of problems. The first one being you get a fairly rough surface, so it is not something you'd want to be selling to people where they're going to be handling it all the time. Probably the biggest drawback of them is structural strength. Because it is layers and layers of plastic, which we can see here, they don't have any strength in the direction of the layers. So if you print something like a ruler, yeah, I'm just hoping this shows, a ruler, and you print it with the layers going vertically in this case, it'd be very easy to snap it if you bend this way, because there isn't a great deal of strength between those joints. So you've got to be careful which way you print it, but they still don't have a great deal of strength. The material you use also has a great impact on that. If you're using something like PLA, that is actually biodegradable and will degrade over time and become brittle. ABS lasts a little bit better. Nylon and other materials are available to last much longer, but you still have that quality issue. Other major disadvantage with 3D printing is time. To print a case like that, if you haven't done 3D printing, my guess would be on a hobbyist type machine, 5 or 6 hours to produce one. So it's not a quick production either. But as I said, very good for seeing that the shape and form fits what you're trying to do. There's also rapid prototyping. Rapid prototyping is something like this. They actually do come out at a quality level that you would expect of a finished product. However, they are intended only, as the name says, for prototyping. They usually are not structurally very strong. Quite often they won't be able to do the function that you want, particularly if you have any moving parts in them. But they will look and feel like the finished item. They aren't overly expensive either, but they're great for samples and other things. Another couple is vacuum casting, and luckily I have here something that is vacuum casted. This is actually a raspberry plant, but the container, and if you look at most pots that you get from a nursery, are vacuum formed, usually produced in very, very thin material, so that you heat it up and when the vacuum forms, it draws it down correctly. But again, very, very weak. Normally, the material is not normally very strong, but good for disposable items, medium sort of runs because it is so cheap, and things that really don't need a great deal of structural strength. The best form for large production would probably be the injection molding. We've got an example of an injection molded chess piece here. When you're injection molding cases, they become very, very cheap. However, to start up an injection molding machine, they will laugh at you if you say you want anything less than, say, 5,000 items, because it's not worth them even starting the machine for that. So it's only useful in very large runs. The other drawback with it is this little piece, the actual die that you have to create to do the molding in. Now, I used to have a company many years ago that made these injection molding device dies. The reason I was involved in that is I'd actually developed a robotic system to mill these devices out. We would start our prices at around $40,000 a mold, 40,000 Australian dollars a mold. So if you're looking at your production run, you've got to recoup that $40,000 over the production life of your device. And that means it's a fairly hefty investment to begin with. I will again say they don't cost anything like that now. I don't know how much they are, but you still have a very large setup cost and a requirement to run off very large numbers of your device, your casing, to make it viable. But they do produce very, very high quality going back to this fella, that would be injection molded. And most of the plastics that you have around you, either in electronics or in household goods, would be either vacuum cast or injection molded. There is that other method that we saw out at who was it? We were doing the temperature sensing, environment sensing around their mold.
Oh yeah,
They do roll molding.
yeah.
That's for extremely large uh, plastic drums and things like that.
Hmm.
Any comments on that, Sebash?
It was very big and very hot,
Yeah,
I
yeah.
would say, yeah.
What was it, about 4 meter cubed?
Yeah, very large. So it was actually an IoT type project that they wanted to do because basically the way the process worked is that big huge canister of the material would go inside the oven to be cooked, and then it would come out on the other side. And they wanted to monitor the ambient temperature of it when it comes out, and
Yeah,
if
the
there,
airflow,
yeah, and the airflow and that type of
that moisture that
information.
they were spraying.
Hmm.
Yeah. Okay, so we've got many options for creating our cases, all dependent on product run, the number you're going to produce, the kind of environment you're going to be putting it in. Is it indoors? Is it industrial? Does it have to be safe for any electricity that you've got floating around inside the box? Um, of course, you need the EMC, the electromagnetic certification. Make sure it's not radiating out lots of electromagnetic interference and many other things to consider. So that's all we have for tonight. We've gone right up to the end, haven't we? Has anyone got any questions, any comments, something they'd like to ask? We're here to help, honestly.
Go ahead, Arvind.
I'll stop sharing my screen.
I had a question also about the project I was working on. Is that okay?
Yeah, go ahead.
Oh, okay. I was wondering because I was looking at that IC that you were talking about, the programmable sensor conditioner. Um, is there some kind of IC like that that would be able to handle the entire plucking process? Um, because I saw that like the manufacturers of the piezometer, they have an auto resonant piezometer, like and it has a small board in there, but I wasn't able to find any kind of chip by Texas Instruments that would do that, where you power it and it handles all of the plucking, and then you just get it has a frequency counter, and you can take the output to your ADC or to your microcontroller.
So what's this counting exactly, Sebash? Muted, I think. Hang on. You muted.
Sorry. Yeah, so this is that standalone project that he's working on where he was plugging the signal to, I think it was from 5 to 2.2, if I'm not mistaken, for that slurry
Yeah,
monitoring
the
process.
negative 2.5 to 2.5 plucking. Um, but I was wondering if there like some kind of a IC like the one you showed me that would
Hmm.
um be able to do all of the like do the entire process of plucking the
Oh,
piezometer.
Um, I,
hang on. What about your FPGAs?
yeah, but I wonder if that would add too much of a cost to what he's looking at. Well, might be a bit of an overkill, but if you look at an FPGA implementation of it, so what FPGAs are, if you're not familiar, they're basically, we call them, they're field programmable gate arrays. So with these specific signal conditioning type projects, they work pretty well. Like if you're dealing with kind of very quick responses to signals and things where you have these critical timings. Um, So, but I wonder if the size of it is gonna cost a problem if he's looking for maybe just a small IC that does.
Going outside of the development boards,
Mhm.
hang on. So if you ignore well, if you take out the cost of the development board, I'm just looking for something that's gone. The FPGA itself isn't expensive.
Hmm.
Well, it depends how much you replace, because you probably wouldn't just replace the picking up of that plucking and reverberation that you get. You could actually replace a lot more of the system with that. And if you look at the low end FPGAs, skip that over. Yeah, we'd have to have a closer look. I think it'd certainly be worth exploring.
Hmm.
Yeah.
There's the Arrow Max 100. It's Max 10.
I did find one thing on AliExpress, but it's like I don't know anything about this manufacturer. Actually, I can share it in here.
Yep. Is that the link? Okay.
Yeah.
Let me
But I
see.
don't. Uh, there's not much information about it. But that's why I was wondering if there was something like this made by someone
Vibrating wire Max Precision module embedded plug-in dual purpose measurement vibrating sensor.
We don't talk about FPGAs in this, do we?
No.
Maybe you should do a little FPGA talk at FPGAs are a wonderful thing to build low production run or medium production run systems on a chip. So it may be worth actually running through one of your early FPGA lectures.
Lectures.
Part of it.
Okay. Yeah, I'll take a look at the
Hmm.
FTD slides. Um, hmm. I'll bookmark this in my browser and I'll take a look to see if I can find something similar to what you're sharing here. A cheap FPGA version of that could be something like this. This Arrow Max 100. Is it available actually for purchase?
Or from AliExpress. Yeah, I wouldn't get anything from
Oh.
AliExpress, honestly.
Yeah.
Yeah, I could not even find this manufacturer, but this
Yeah.
was what I thought I wanted something like this, but I couldn't find it by Texas Instruments or any larger manufacturer.
Take a look at the one I sent that might be able. Well, it doesn't do specifically that, but the thing is, because it's an FPGA, you can implement that functionality in there. I'm just trying to see what the cost of it is. Because I know the development, not the development, the educational kit in version of that is about $70. But this is an evaluation board for a DE for a Max 10 FPGA. Technology SDRAM iOS 2. See if I can find the only issue I can see is if you do find a chip that's specialized, it would probably be out of stock because of the chip shortage. So actually exploring the FPGA route might be a viable solution. See if I can find a Anyway, they're selling it. This is from Arrow. Download data sheet. Sorry.
While you're doing that, has anyone else got questions? Feel free to speak up. Raise your hand. Arun, yes.
It's me again. So my next question is about the audio recognition.
Sorry, Harun, we don't hear your audio very well.
Is still bad.
We are getting multiple packets, I think. Yeah.
Oh, really?
Can you type it, or is it a bit long for that?
1 second. Is there any difference now?
Yeah, that's much better.
Yeah.
Okay, just use the headphones. My question is about the audio recognition. It might be a little bit off topic, so please warn me if it is.
Huh.
I've been trying to recognize a certain pattern sounds like small clicks or the small sliding sounds. And so far, I could only find as a library, as a help, this edge impulse. But it seems a bit only compatible with the one Arduino. It was the BLE Sense 33. And a couple of other very, very big boards. But what I wanted to do was something much more compact, and I wanted to actually program my own chip. I saw that this, especially at Mega 2560, it has barely enough processing power to process some audio files. Other than that, I should go ARM Cortex, but it's a little bit above my head, I think, at this point. So is there any suggestion that you can make to push me in the right direction?
Yeah. So you're trying to recognize clicking sounds? Is that it?
Yes.
Like a key tap or something similar coming through on an audio file?
Yes, let's say like this, I'm trying to use these industrial clips, and almost every and each clip has a unique sound because of their size and the material when they insert it in the socket correctly. So I'm trying to recognize this sound in an industrial environment for the line workers. And yeah, that's basically it.
Lots of background noise?
Yes.
Okay. That's going to be hard and complex because it's completely doable. And there's a variety of ways you could look at it. My first thought would be using a microphone array for a start. So do you know where the source of the sound is?
You mean, sorry, what do you mean? Like source of the sound? Where is it?
Where is the sound coming from? Is there a particular location that's generating that sound?
I'm trying to attach a microphone on the fingertip with an extension, so it's going to be right next to the clip. The sound, is that what you meant?
Yeah.
Or
yeah, that's right. So what you could do is you look at having the microphone that's on the fingertip and picking up the click, but additionally you would have other microphones that would pick up the surrounding noise, so away from the fingertip. You then just subtract that external signal after normalizing them to the same sort of level from the signal you're getting from the microphone on the fingertip. And in that way, you should end up with the majority of your signal just being the microphone, the click that you're getting from that fingertip. Then it's a question of identifying what that click is like. So my first way of looking at it is to do an FFT on it, look at the frequencies, find the frequency components of the click that you're looking for, and threshold on the level of that particular frequency for those different clicks, and then maybe set up a fuzzy logic system which requires very, very little processing power to determine which group of or which category of click it belongs to.
I see. I see.
Fuzzy logic can be implemented just in a lookup table, which is why once you've worked out each of the decision areas, I've forgotten what they're called, it becomes very easy to actually implement in a very low power system. But that
I see. I see.
separating the click from background noise is not a minor problem.
Mm-hmm. I was just counting on the fact that the microphone is going to be very close to the source, and so that's why maybe it might be identifiable. But anyways, that's not the only way to detect it. It's going to be a combination of 3 or 4 other elements. So in the end, it's going to be an and or, but it would be a nice extra. So the machine learning is absolutely not necessary in this case. Would that be correct? Like it
I
can
would
be
say
done
you don't
also
need to,
just.
no.
Uh-huh. Mhm.
You could, certainly one way of going. I would tend to go back to the more traditional methods like fuzzy logic. So you have a certain level of certainty of which click it's going to be.
Mhm.
But I'm thinking, is it the click? How do you think it'd go with an IMU? Because the click would, if the person's actually using their hand to push the connector in, would there be enough vibration from an IMU on the fingertip to pick up that better than the sound? I'm asking Sebastian, you're the IMU guy.
I have tried before with accelerometer, but there were a lot of confusion with the normal hand movements, especially changes from person to person. The biggest problem was actually the habits of people.
Yeah.
Like some people had the habit of cracking their, for example, these finger joints during the work time, of course. And others, if they hit the hand a little bit in the just right amount of the power, it would get a wrong signal. So the accelerometer really didn't work. But yeah, for now, it's the best way is the using an FSR on the fingertip itself, and some inductive sensor to recognize the clip itself. And the third one would be the microphone normally for me.
And you're really looking to see if the clip's in correctly, so a vision system's probably out of the question and probably too pricey as well.
I mean, the price is, okay, it's a bit cocky to say it, but the price is really not important in this case because I have the company backing up the project. But with the, sorry, I cannot find the words. English is not very good.
I don't suppose you could shoot a recording of this sound through at some point?
Yeah. It has a distinctive frequency. I was able to, this Edge Impulse website that I was saying that when I tried to use it, it was able to distinguish it. I was able to run it through machine learning, for example. Then when I used the samples within the website, the recorded ones, it's with the 90% accuracy, it was able to detect it even with the background noise with a simple microphone that's these 50-cent microphones. So I know that it can be done, but the machine learning is way over my head. So that's why
So
I was looking for a little bit easier way.
Have
with
you
that
looked at
edge impulse.
TinyML at all?
Sorry, go ahead, Ian.
I was just going to say, have you looked at TinyML at all? Because that's relatively simple to use.
No, never used that. I can have a look at that.
Because you can actually get chips which are optimized to run TinyML.
Mm-hmm. Okay.
I would say that, and sorry, just I didn't get so with Edge Impulse, and I think that voice recognition system that we were talking about, the offline one, that uses a subset of that Edge Impulse. What was the issue that it's only tied down to a particular type of microcontroller that you were worried about?
It is tied down to only Arduino 33BLE Sense, the name was, I think. It was only
Yeah.
tied down to this. I can sure use this one,
Hmm.
but what I wanted to do was to build my own circuit on a flex PCB style on this polymer.
Right.
So the PCB board can be actually wrapped around the wrist. So it would be weightless and it would have zero strains on the user instead of having a giant PCB board somewhere around.
Hmm.
Mm.
So this is why I wanted to build my own, let's say, the PCB environment.
Well, you could. One of the things you could do is you can,
Hang on.
because Arduino does provide the specifications for the board you're talking about, saying if it would be worth it. That's probably an overkill to take that. I know because I know the board you're talking about. That's the one we were initially using because it has enough processing power to do the. It does three-phase audio detection. Yeah, I was just thinking maybe you can get the guts of that, remove the peripherals that you don't need, just keep the essential processor and the things that you need, and then design it in the because it would be the same processor, so it would still support the library, but you just remove the peripherals on the board that you don't need. Maybe say if you don't need the Bluetooth, remove that, and then lay it on the flexible PCB.
There's also the option of actually transferring the audio via Bluetooth link, right, and have the processing done in a thing, drop in your pocket, clip on your belt.
Okay, I see. Yeah, that was my yeah, as a last resort, I was planning that. I already actually kind of done the design of that one with the using this. It uses, I think, ARM Cortex chip. So yeah, the only problem is I wasn't very familiar with the ARM Cortex and the programming of it. So that's why I was looking for a little bit lower grade, let's say, Atmega chips. For me, of course, relatively easier to use.
Yeah, I was just
But
looking at
it's of course very feasible. Sorry.
I was just looking at the Edge Impulse site, and that is actually TinyML.
Yeah, it is TinyML based.
Yep.
They made a wonderful website. It works very nice. I already made my test and it was very successful. Just I was looking for an alternative if possible.
Yeah, my alternative would probably actually be the same thing, but as a native TinyML platform.
Okay, clear for me.
Okay. Anyone else got anything they'd like to add, subtract, multiply? If not, I'll stop the recording.